Swayam Prabha. Digital India. Educated India.
Hello and welcome to all of you after a long break. In the previous lecture, we were discussing RC circuits. Before that, we had only considered circuits with resistors, which have no memory. So that means that to evaluate what happens with a time varying signal, you just have to calculate point by point. Okay. And also, all the equations we got while analyzing resistive circuits were algebraic equations. Okay. Now, when you have a capacitor or an inductor, you end up with, when we have resistors only, we will have algebraic equations, and when we have capacitors or inductors, we will end up with differential equations. So that's what we solved, and we solved it for a couple of cases. Capacitor had some initial condition, and the input was 0, and then we took a case where the capacitor initially had a 0 initial condition, and we applied a step input. Okay, so now we'll continue from there. We saw what happens in this case. C, and the input Vs goes from 0 to Vp, I think I called it. Let me check. Yeah. Zero to Vp at t equal to 0. Okay. Now, in this case, we saw that the capacitor voltage Vc is given by Vc of t equals Vp times 1 minus exponential minus t by Rc. Okay. So, and the assumption of course was that the capacitor here is initially, that means for t less than 0, discharged. Okay, so this was what we got. Okay, so the general form of the expression turned out to be of this type. Okay. It was of this type where Vc of t would be Vp, the applied voltage, plus some exponential. Okay, and this coefficient V0 had to be calculated from initial conditions. Okay, now in this particular case, we know that the initial condition on the capacitor is 0. Okay, we will discuss more the business of initial conditions, and so at t equal to 0, Vp plus V0 will be the output voltage, and that has to be equal to 0. So V0 turns out to be minus Vp, giving you this expression. Okay, so if you start from a different initial condition, of course you will have a different value of V0. Okay, so is this clear? Are there any questions on this first order RC circuit, how we analyzed it, the result that we have got? Any of that stuff? And when we had a zero input and an initial condition, this is what we analyzed first. We have C and R, okay, and the voltage across the capacitor turns out to be the initial condition on the capacitor times exponential minus T by RC, okay. So if we combine the two cases, that is, let me say that I have this circuit, and the initial condition equals Vc of 0. Okay. So what is the expression for Vc of t in this case? Please try to answer this. Here I am talking about a case where at t equal to 0, Vs jumps from 0 to Vp. But the capacitor is not initially discharged. At t equal to 0, it has an initial condition of Vc of 0. Okay. So what is the expression for Vc of t? Please answer this. Please try to answer this one. So all you have to do is to take the previous expression, that is Vc of t equals Vp plus V0 exponential minus T by Rc, okay, and adjust the value of V0 for the appropriate initial condition, okay. So let me do it here. Then Vc of t is Vp plus this whole expression. So Vc of 0 would be Vp plus V0, and this should be equal to Vc of 0. Okay. So V0 would be Vp minus Vc of 0. Okay. So the expression for Vc of t would be Vp plus Vp minus Vc of 0 exponential minus T by Rc. Okay. So this is the expression. I think I made a mistake in this. It should be the negative of this. Vc of 0 minus Vp, and here also it is Vc of 0 minus Vp. Okay. So now this we'll spend some time discussing this equation. This is the general form of equation of the step response, that is response to a stepped input, whether it be voltage or current, for an RC circuit, for a first order circuit. Okay, the RC circuit we have is an example of a first order circuit. By first order, what I mean is the equation describing this is a first order differential equation. Okay, so let's look at this some more carefully. Okay, now this RC, by the way, is the time constant, and this minus 1 by RC equals P1. This is the characteristic frequency. Okay. So now you have noticed that for all the cases we calculated, we end up with this exponential minus t by RC in the response. Okay. Now this turns out to be a general property of linear systems, that the response will consist of exponential of characteristic frequency times the time. Okay. So exponential P1t, this will form a part of the response of any linear first order system. Okay. In fact, all linear systems have this behavior. If you don't have a first order system, if you have a higher order system, you will end up with multiple exponentials, exponential of P1t, exponential of P2t, and so on. Okay. So now this can be thought of as two parts. This part, which is dependent solely on the input, this is known as the forced response or the steady state response, and this part, which has this exponential minus t by RC, which is a characteristic of the circuit, is known as the natural response. Or the transient response. Okay. So the natural response of any linear system will be of the form of exponential minus t by RC. There are some small modifications which we will not go into, but this is generally the case. Okay. And the total response always consists of forced response, which depends solely on the input, that is the driving function or the forcing function, and the natural response, which depends on initial conditions and the forcing function and the natural response of the circuit of the form exponential minus t by RC. Okay. Now, so let me also write this. So this forced response or steady state response depends only on the input, which is the forcing function. Okay, and this natural response will always have this term exponential minus t by RC, which by the way is also known as the natural mode. Okay, so just like you would have a string with a characteristic frequency, right? If you pluck a string, it will vibrate at some frequency. That's called one of the modes of a string. This exponential minus t by RC is the mode of the first order RC circuit. Okay, so all linear system response can be classified into the forced response and the natural response, or equivalently the steady state response and transient response. And another terminology you hear, particularly in relation to differential equations in mathematics, is this is the solution to homogeneous equation, and this is the particular integral. Okay, so these are the same thing and these all mean the same thing. Okay, this is a general property of all linear systems, and of course we are now looking at a first order RC circuit. Okay, now we can also rewrite this as Vp times 1 minus exponential minus t by RC plus Vc of 0 exponential minus t by RC. Okay, so you can see that this part is proportional to the input. Okay, and it doesn't have any initial condition term in it. In fact, this is known as the zero state response. Okay, so this is the response you would have got if the state of the capacitor, the initial condition on the capacitor, were to be 0. Okay, and this part, which depends only on the initial condition, is known as the zero input response. Okay, now the reason for this terminology is obvious. The zero state response is the response you get when the initial state is 0, and the zero input response is the response you get when the input Vp is 0. By the way, I have to caution once more that we are only considering a case of a piecewise constant input. What I mean by that is the input is not arbitrarily varying with time. It varies from 0 to Vp. Okay, it jumps from one particular constant value to another particular constant value. What I am particularly warning against here is that if let's say Vp were to do this, Vp were doing something of this sort, okay, you should not substitute Vp of t in this expression. Okay, that is completely wrong. You will get some integral with Vp inside it. You can't simply substitute Vp of t. This is for a step of Vp. Okay. Now, this is supposed to be a linear system, and the response we classified into different parts. Okay, so we have a number of things. First of all, we have the total response, which is Vc of t, and we have the transient response. We have the steady state response, response and 0 input response. And all of this is for a system which we know is linear. At least we know that it's made of linear components, resistor and capacitor. Okay. So now my question is, what does linearity mean in this case? Okay. That is one way to express linearity is to say that some response is proportional to some input, okay, or something is proportional to something else. Now please try to answer this, like, is the total response linear with the input? Is this linear? Yes or no? You can type your answers into the chat window. Or I can pose the same question in a different way. We have all these different types of responses, or the total response was classified into these different things. Okay. So let me put down these things. Which of these is linear with the input? You can also indicate your choices on the poll that has appeared. Now I have listed 5 responses, all either the total response or part of the total response of a first order RC circuit. My question is, which of this is linear with the input to the RC circuit? And of course we are only considering step inputs at this time. Please try to answer this. In fact, all you have to do is to look at the expressions for these. Okay, so the expression for the total response is Vp plus Vc of 0 minus Vp exponential minus T by Rc. The transient response is Vc of 0 minus Vp exponential minus T by Rc. The steady state response is Vp The zero state response is Vp 1 minus exponential minus t by Rc. And finally, the zero input response is Vc of 0 exponential minus t by Rc. Okay. So now from this you should be able to very easily tell which of these is directly proportional to the input. Okay. Okay, now I got some responses. Okay, clearly the first one is not proportional to Vp because of this Vc of 0 term. So this is also not proportional to Vp because of this Vc of 0 term. So the steady state response and the zero state response, these are proportional to Vp. Okay, so these will be linear with the input. Okay, and similarly this one I didn't ask that question, but this part, the zero input response, will be linear with the initial condition. Okay, so this is what linearity means in this particular context. The total response will not be linear with either the input or the initial condition in general. Okay, if Vc of 0 happens to be 0, that's a different matter, that's a coincidence. Otherwise, the total response or the transient response will not be linear with either the input or the initial condition. The steady state response will be linear with the input because it depends only on the input, and the zero state response also depends only on the input, and it will be linear with the input. And the zero input response will be proportional to or linear with the initial condition. Okay. So that's what linearity means in this context. Okay. I mentioned this because we know that in linear systems the response is proportional to the input. If you have a resistive circuit, you change an input, then the response will change in proportion to that input. Okay. I'm assuming a circuit with a single input. Now, in case of these circuits which have memory elements like capacitors or inductors, the situation is a little more complicated, and it is linear in this particular sense. Okay. Now we can also go ahead and interpret this equation further. First of all, if I plot this, let's say it starts from some Vc of 0 and reaches a steady state of Vp. Okay, because at t equal to 0, we can see that this Vc of t will be Vc of 0, and at t equal to infinity, when the exponential has died out, it is equal to Vp. Okay. So the response goes as an exponential and finally reaches Vp. Okay. So there are different ways to interpret this. If you look at this part of it, this is the difference between final or initial and final values. Okay, and this whole term, if you look at it,